Hello, everyone. My name is Berrak Sisman. I am from the Singapore University of Technology and Design in Singapore. Today, I will be talking about our paper called Generative Adversarial Networks for Singing Voice Conversion with and without parallel training data. We have conducted this research together with my colleague Haizhou from the National University of Singapore. Let's start with the basic definition of singing voice conversion. It is a task to convert one singer's voice to sound like that of another without changing the lyrical content. Here, you can also see an illustration of it. We have a source singer who is singing Mamma Mia, Here I Go Again, and we will conduct singing voice conversion here, and we are going to change the identity of this person so that it sounds like this lady is singing the same song. And I would like to highlight that singing conveys lexical and emotional information through words and tones. Both are to be transferred from the source to the target speaker. So in this paper, we will propose novel solutions to singing voice conversion based on generative adversarial networks with and without parallel training data. Let's briefly talk about singing voice conversion. Singing voice conversion is not a very easy task because singing itself is not an easy task, and to mimic someone singing is more difficult. While professional singers are trained to control and vary their vocal timbres, they are bounded by the physical limit of human vocal production system. And singing voice conversion provides an extension to one's vocal ability to control the voice beyond the physical limit and express it in an extended variety of ways. So singing voice conversion has lots of applications, and some of them are listed here, such as singing synthesis, dubbing of soundtrack, and perfect one singing. And there is also a challenge here that I would like to highlight. Singing is a form of art, and any distortion on the converted singing voice cannot be tolerated. So when I say singing voice conversion, you may all think like there is also voice conversion. What is the difference between singing voice conversion and the traditional voice conversion? Well, they share similar motivation with the conventional speech voice conversion, which we also call it identity conversion. But singing voice conversion differs from speech voice conversion in many ways that are listed here. To start with, in the traditional speech voice conversion, speech prosody that includes pitch, dynamics, duration of words, they all describe the speaker individuality. Therefore, we need to transform from the source to the target speaker. On the other hand, in singing voice conversion, the manner of singing is primarily determined by the sheet music itself, so it is considered as person independent. Therefore, in singing voice conversion, only the characteristics of voice identity, such as timbre, are considered as the person-dependent traits to be converted. So in this paper, we will only focus on the spectrum conversion aspect of singing voice conversion. So before starting to talk about our proposed singing voice conversion models, I would like to very briefly talk about generative adversarial networks and why we choose them in this paper. So the traditional generative adversarial network consists of a generator and a discriminator, and many of you may already know this. And generative adversarial networks have recently been shown to be effective in so many fields listed below: image generation, image translation, speech enhancement, language identification, text-to-speech synthesis, and even in speech voice conversion. And here in this paper, we propose a generative adversarial network that works for high-quality singing voice conversion, both with and without parallel training data. So I would like to list our contributions here. To start with, we propose a singing voice conversion framework that is based on generative adversarial networks. And we achieve high-quality converted singing voice without any external process, such as speech recognition, which is not very easy to train. And by using cycle GAN, we achieve high-quality parallel data-free singing voice that outperforms the baseline. And last but not least, we reduce the reliance on large amount of data for both parallel and non-parallel training scenarios. We would like to note that this paper reports the first successful attempt to use generative adversarial networks for parallel data singing voice conversion. So let's start with singing voice conversion with parallel training data. The statistical methods, such as Gaussian mixture models, represent an early success of singing voice conversion. We have also listed some of these works here. They are all great ideas, but they do not use deep learning most of the time. And the furtherance in deep learning has a positive impact in many fields, with no exception to singing voice conversion. And here in this paper, we propose to use GANs to learn the essential differences between the source singing and the original target singing through a discriminative process denoted as SINGAN. And in this paper, we further the study of a SINGAN as a part of the GAN solutions to singing voice conversion in a comparative study. So let's start with the training phase of the SINGAN. We are going to have three main steps provided here. The first step is to perform world analysis to obtain the spectral and prosody features as provided here with the blue box. And the second step is to use dynamic time warping algorithm for temporal alignment of source and target singing spectral features. That is also provided here with a blue color. Blue color here represents the algorithms that we cannot train. And the last step is to train the generative adversarial networks by using the aligned singing source and target features. I would like to highlight here one more time that we have data from source and target singers, and they are singing the same song. So this is considered parallel training data for singing voice conversion. And we also would like to highlight that the previous studies taught us in intragender singing voice conversion, it is not always necessary to transform the F0 values from the source to the target singer, mainly because both singers often sing on key. And the conversion of aperiodicity usually has only a small impact on the converted singing voice. So therefore, in this paper, we only perform spectral feature conversion to achieve acceptable singing voice quality. And when it comes to runtime conversion, we again have three main steps provided here. The first step is to obtain source singing features using the world analysis. And the second step is to generate the converted singing spectral features by using the GAN, which is already trained during the training phase. And last but not least, we are going to generate the converted singing waveform by using world synthesis. And I would like to highlight that in this paper, as stated by the previous studies, we do not perform F0 conversion for intragender singing voice conversion experiments. And for intergender singing voice conversion experiments, we perform linear F0 conversion. And in all experiments that we have in this paper, we copy the aperiodicity of the source singing to the target. So this is the end of the parallel data case. Let's now focus on singing voice conversion without parallel training data. And before we discuss singing voice conversion, I want to highlight something. Cycle GAN can learn from non-parallel training data, as also cited here, and it achieves high-quality voice conversion, speech voice conversion, and it also provides a solution to model the singer translation. And to our best knowledge, CycleGAN has not been studied for singing voice conversion yet. And in this paper, CycleGAN is trained to find an optimal pseudo pair from the unpaired singing data of two speakers. Our cycle GAN for singing voice conversion uses cycle consistency loss, adversarial loss, and an identity mapping loss. And we configure the cycle GAN with gated CNNs and train it with an identity mapping loss here. This will allow us to preserve the lyrical content of the source singer. So in the next slides, we will be discussing very briefly why we need these loss functions. Let's start with why we need adversarial loss. In singing voice conversion, our aim is to optimize the distribution of the converted singing features as much as closer to the distribution of target singer. And the closer the distribution of converted data becomes to that of target singer, the smaller the loss becomes. Hence, we can achieve high speaker similarity in singing voice conversion. So then why we need cycle consistency loss? The reason is the adversarial loss only tells us whether the conversion follows the target singer's data distribution and does not help to preserve the source singer's contextual information. And with cycle consistency loss, we can help maintain the contextual information between the source and target pair. And why identity mapping loss? Because a cycle consistency loss provides constraints on a structure. However, it would not suffice to guarantee that the mappings always preserve lyrical content of the source singer. So, to explicitly preserve the lyrical content, we are going to incorporate an identity mapping loss here. Let's look at the experiments. Throughout this paper, we perform objective and subjective evaluation with NUS singing database, and this corpus consists of audio recordings from 48 English songs by 12 professional singers. And for both parallel and non-parallel training data settings, we conduct experiments with 3 and 5 source target singing pairs. And we extract 34 Malcapstral coefficients, logarithmic fundamental frequency, and a periodicity. And we normalize the source and target MCAPs to zero mean and unit variance by using the statistics of the training set. So let's look at the objective evaluation here. We adopt Malcapstral distortion between the target singer's natural singing and the converted ones. And as you may all know, a lower Malcapstral distortion value indicates smaller spectral distortion. And here in this table 1, we will report 3 frameworks. And if you are personally interested how we train these networks, please note that all these models and experimental conditions are provided in the paper. So you can just go and check. For each of them, we provided more than one paragraph and explain how we train them. And for each of them, we train male-to-male and female-to-male conversions. And for DNN and GAN, we are going to use parallel training data, 3 songs from each speaker and 5 songs from each speaker. And if you just compare DNN and GAN, you are going to observe that GAN always outperforms DNN. So this shows that if we have parallel training data, GAN is a much better solution than DNN for singing voice conversion. And let's look at cycle GAN now. Cycle GAN's problem is more challenging because we are doing non-parallel singing voice conversion, which means the lyrical content is different during the training. But even though the data is non-parallel, cycle GAN achieves comparable results or sometimes even better results than the DNN baseline. And I want to note that DNN baseline uses parallel data. So these results show that GAN achieves much better results than DNN with parallel data. And even if we do not have parallel data, we can still use cycle GAN and achieve comparable or even better results to that of DNN. So in the next slide here, we reported subjective evaluation. We have more experiments in the paper, but due to the interest of time, I only take some of them here in the presentation. So we reported mean opinion score, and we have 15 subjects participated in the listening test, and each subject listens to 50 converted singing voices. And DNN and GAN are trained with parallel data, whereas cycle GAN is trained with non-parallel training data. And if you just compare DNN and GAN, you are going to observe that GAN outperforms DNN a lot, and even though they use the same amount of parallel training data. So this result shows us that GAN outperforms DNN, and it should be used for singing voice conversion over DNN. And if you look at cycle GAN is trained with the same amount of training data, but it is non-parallel, which means it is a more challenging task. And even for a more challenging task, cycle GAN still achieves a very similar performance to that of DNN, where DNN uses parallel training data. So we believe that the performance of cycle GAN here is remarkable, assuming that it uses non-parallel training data. So another experiment that we want to compare here is cycle GAN versus GAN for speaker similarity. And in this experiment reported here, this is a preference test for speaker similarity. We use 5 non-parallel song pairs for cycle GAN training, whereas we only use 3 parallel song pairs for GAN training. And here, this experiment shows that cycle GAN with singing data, with non-parallel singing data, this pink bar, achieves comparable results to GAN with parallel singing data. as it is chosen as the better sample for 48.1% of the time, which we believe is remarkable because, as you know, having non-parallel training data is a much more challenging task than having a parallel training data setup. So we believe that CycleGAN achieves really good performance in terms of singing voice conversion when you have non-parallel training data. So to sum up, in this paper, we propose novel solutions based on generative adversarial networks to singing voice conversion with and without parallel training data. And the proposed GAN framework achieves high-quality converted singing voice with parallel training data. By using cycle GAN, we estimate an optimal pseudo pair between source and target singers. And even when we have non-parallel training data, we show that it works pretty well. And furthermore, we also show that the proposed GAN framework performs better with less training data than DNN, which we believe really remarkable. So last but not least, with or without parallel training data available, generative adversarial networks achieve high quality synthesized singing voice. Thank you for listening.